So welcome. So this is our section on vectors, and what we're going to do today. Well, we can define any point in space using a system of coordinates. We knew that before. Cartesian, plane polar, we probably touched on those before. And then a system of coordinates defines a frame of reference. It's probably a new term to us, but it just means, how do you measure things? Do you measure things relative to the train, or do you measure things relative to the person? Do you measure things relative to the sun or relative to the earth? It depends on what you want to do. But you've got to know what you're doing in that. And then we divide the world up into scalars and vectors. And you've probably already come across the fact that scalars have just magnitude. So my mass is a scalar. It's like I don't have mass in a direction. I have mass. It's just what I have. My age is a scalar. It's like. But other things like my weight is a force, and it points towards the center of the earth. It's not a force upwards or a force over there. It points towards the center of the earth. Velocity is a vector because it points in a certain direction. But I would say that speed is not, because speed is just how fast you're going no matter which direction you go. Temperature is a scalar, because although there's positives and negatives, when you use positives and negatives on the number line to talk about directions, with temperature we're just saying above zero and below zero. The difference is that we treat them kind of mathematically differently. Vectors have magnitude and direction, and scalars only have magnitude. And it's useful throughout physics to divide the world up and say, a new parameter comes in, is this a scalar or is this a vector? You're going to do momentum, that's going to be a vector. You're going to do impulse, that's going to be a vector. We deal a lot with vectors. And the payoff is, what we find is that because the vector includes magnitude and direction, if we get kind of good math skills like doing a dot product and a cross product, have you come across those yet? So cross products are amazing. Cross products which work with vectors enable you to take two vectors and you can get the vector answer for some really complicated things without any visualization. And if you try to do that using diagrams, you can do it. But it's much, much harder. So everything you get is designed to make life easier, to make us more powerful with the least effort possible. And so unlike me when I was a student, I saw everything as a liability, like, will I be able to do this? And I didn't think of it from a positive point of view of, man, with this I'll be able to do so much more. So embrace new things. I always tended to put off and can I do it the old way? Forget that. If you could do it the old way, we wouldn't do the new way. It's like you don't stay in a textbook if you're useless. You only stay in a textbook if you're valuable. So embrace these things. So scalars and vectors, at the back of your mind, just always put, every time there's a new parameter, I've got to ask myself, is it a vector or is it a scalar? And then we can sum vector parameters using vector diagrams. That's one way of summing vector diagrams. We know how to add scalars, of course. You add the numbers together. We've done that for years, but now we're doing adding vectors. If we want to go a bit more precise, then it might be an idea to use trigonometry. So we'd go from doing a vector diagram, which works, but it's a little bit rough and ready. We'd go to using components. We'd break each vector up into an x component and a y component. Then we can add all the x's up to get the x of our answer. We can add all the y's up to get the y of our answer. Then we can figure out what the final vector is. So it's a procedural thing which really helps us. And then the next thing we do is we can use vector components to sum parameters. That's what I just described. And then the problem with components is that they really get bogged down unless you, for 3 dimensions, unless you have a really good way of keeping things in order. It's bookkeeping at that point. With components, I'm going to try and persuade you to only do x components together and not talk about y components. And then I'm going to try and get you to only do y components together and not talk about x components. But for 3 dimensions, then you've got x, y, and z, and there's angles that get messed up and all that. And somebody came up with this thing about, it's bookkeeping. It's like, let's call these IJK vectors. And I remember I'd struggled with components, but then I'd sorted it out, and I was really strong at them. And I said, I don't need this. Because every example they gave for IJK vectors was two-dimensional. I could kill them in 2 dimensions. And then later on, they gave me a 3-dimensional problem, and man, I was filling the page with writing and losing track of things, and I needed the IJK vectors. So I'm going to try and give you some 3-dimensional problems in IJK and try and convince you that they are just like, it's such a good system. We call this physics with calculus, but to some extent it should be physics with IJK, because we use IJKs a lot. Okay. So scalar. Scalar has magnitude but not direction. Examples are temperature and mass. And speed. You know, speed would also be distance traveled. You know, all those kind of things. And then vectors, well, we've got displacement, velocity, acceleration, force, you know, weight or whatever. That's a vector. You've got to ask yourself, does it have direction in space, in a room? And, you know, the fact that at that point in space we have minus 20 degrees just means it's cold. It doesn't mean to say there's a vector. You know, the minus and the plus does not mean vector. You know, it just means above and below the 0 on that scale. So you've got to do a little bit of thinking about the context. A little bit of just practice, really. I'm sure you've done this at some point, and that is basically we can define a point in space. We're going to talk about 2-dimensional space. We can define a point in space by basically, well, what do we need? We need some kind of fixed reference point, which we call the origin. You do need that. You've got to know where you start counting from. So in both the Cartesian coordinate system named after Descartes and the plane polar coordinate system, we have an origin. And then we need some kind of axis or axes. And in the Cartesian coordinate, the idea is we divide it up into x and we divide it up into y. And in 3 dimensions, we could even do a z. Now, there's an issue right off the bat, because if you've done math, I think you basically get your axes and you just lay them down. You've got a different way of typically drawing your diagrams. It's the same, we call it a right-handed orthogonal system. It's the same system, but in physics, we tend to always look at them with x across the page and y up and down the page and z coming out and hitting you in the nose. And in math, they don't always do that. And so people sometimes get uncomfortable, and rightly so. It's unfortunate that the 2 traditions are somewhat different. Someone's got to change, and we've not blinked and they've not blinked, so we're both kind of standing our own ground. But just be mindful of that. If you just glance at your axes, you might, and you're really practiced in the math method, you might take what you think is a y-axis and call it a z-axis, or vice versa. So watch out for that. But we need some kind of axis, and over here we have just basically an axis which we typically draw as a positive x-going axis. And then we need instructions, and these are made by people. If you've got a space alien, they would not necessarily have the same instructions. In our instructions, good old Descartes said, see how far you need to go along the x-axis, and then see how far you need to go along the y-axis, and separate them with a column. So we have, our x component. I'm going to draw that like that. There's my, how far along this axis did I go? Let's count and write that 5 down there. And then how far along my y-axis do I need to go? Let's count and write my axis there. I don't need to bother writing down the x and y, because I know that in our tradition, x always comes first, comma, and then y. Yeah? Space aliens didn't have Descartes. They might do it the opposite way, They probably have orthogonal axes, because there's a whole bunch of science reasons why having... I can show you it. The x motion is completely independent from the y motion. I can move here and not affect my y motion. I can just go like that. I can go like that. I'm changing my x, but not changing my y at all. If I went with axes like that, can you see how any motion on my x must also be reflected in motion on this axis? Because I'm moving. It's got to line up. There's a point in space. So these are not independent axes, but these are. And so space aliens would value independent axes the way that we do. The difference is they might have said Y first and then X, so that we need the instructions. By the way, we spend a lot of time, as one of our shortcuts, been conning about where we put our orthogonal axes. Sometimes that's really convenient. That's really, X and Y is really convenient, but sometimes you might want down the slope and perpendicular to the slope. We get all the advantages of an orthogonal axis system, but they fit our problem. So we'll be changing where our axes are all the time, but we'll make sure they're orthogonal so that they're independent of each other. Well, that's one set of rules. Then we have the other set of rules, which is, you basically see how far you need to go along. Again, I keep losing my pen. You need to see how far you need to go along this line, and you write that down. And then you see how many degrees or radians, whatever you like, you need to go from this axis in a counterclockwise direction, starting from the positive x-axis. So there are two systems. And we can designate in 2 dimensions any point on a 2-dimensional plane using these techniques. And so this is just a kind of exercise in this. So we have 3, 4. So 1, 2, 3. 1, 2, 3, 4. So there's my point in space. And by the coordinate systems, Cartesian coordinates is that. And it says, what is this in plane polar systems? So now let me change my colored pen so you can see kind of what I'm doing here. So let's go to a green. There's my point of interest now. And what I can say is that, let's call this R. R squared equals x squared plus y squared. How do I know that? What am I looking at on my diagram that says, oh yeah, you can use Pythagoras on that? I'm looking at a triangle. It's a right triangle, so I can use Pythagoras. So I'm going to say, well, then R is equal to the square root of 3 squared plus 4 squared, which equals square root of 25, which equals 5. And, you know, some people don't ever give you a 3, 4, 5 triangle, and other people give you a lot. The advantage is, with a bit of practice, you realize that 3 squared plus 4 squared equals 5 squared. So it's one of the geometries of a right triangle that people often remember. And if you don't see it, you just work it out. No harm done, just a little bit of time. But what sometimes teachers will do is they'll use a 3, 4, 5 triangle, and you can just see it. I know that's 5 because of 3, 4, 5 triangle. I was thinking back. I'm like on the cusp. My brother's 5 years older than me, so he's like late 60s now. And in his generation, just that 5 years before me, they learned maybe 5 different things. We learned 1. They learned like 5 different special triangles. He seemed to do a lot more rote learning than I did. But you can just go, oh, yeah, that's so and so. You make choices. Then the next thing we need to know is the angle. And here I'm going to use a bit of trig, and I'm going to say, well, the angle theta, so tan theta equals opposite over adjacent. And I look at my diagram and say, well, that's the same as the other side, so that's 4. So that's 4, and that's the same as the bottom, so that's 3. So they say theta is equal to 10 to the minus 1 of 4 over 3. I get my little calculator. The nice thing about these calculators is that they actually tell you what mode they're in on the screen. So I look down and I say, this is in degrees, DEG is in degrees, so I know what I'm doing. And I go second tangent, and I go 4 divided by 3, close my parentheses, and then I get 53.13. So theta is equal to 53.13 degrees. There I have it. If you'd by chance done it in radians, there's no law that says you can't work in radians, but you have to label it as radians. So if I just come along, turns my degrees into radians, do that, so go enter, and I'm going to get 0.92. Either one's acceptable, Only write one down, please. Don't give me two answers, because it leaves me in a real dilemma, especially when they don't agree. Because which one do I take? So if you do write down two answers, I'm going to mark it as wrong. Because I know I taught high school. I had students who gleefully told me that, well, it was either 56 or 72, so I put down 56 over there in a box, and then I put down 72 down there in a box. And if you're just scanning it, you're going to see the 72 because it's right, or you're going to scan it and see the 50. So I started realizing that people are sometimes a lot more mindful than I thought they were. So then I started saying, no, no two answers. Just give me one answer in a box, and I'm happy. So, pick one of those to put in the box, kind of thing. But that's just geometry. So this, I think, is, I like vector diagrams. Vector diagrams are like really kind of cool. They, before computers, aeroplane navigators would basically do what they call dead reckoning. They'd have big charts. They would get wind speed. They'd get velocity of the plane. They'd figure out with that wind speed and that velocity of the plane, we need to go in this direction to get to Paris. And they'd do the calculations using these things. They'd set off, and when they thought they should be near Paris, they'd look around for Paris. Oh, it's over there. Okay, it's no big deal. It's not on this side, it's on that side. It's no big deal. Now we're in Paris. Now let's go. We want to really go to Milan. So from Paris to Milan, with this wind speed, we need to... And they do it, and it works. So don't get the idea that vector diagrams are like, kind of like trivial babyish stuff, but the real stuff involves trig. They're both incredibly useful. And some solutions really lend themselves to vector diagrams. One of my kind of like, sometimes life is just kind to you. And when I first arrived here, I had some students, and they were doing math with one of the math teachers, and she'd given them a bear of a problem. It was like, it was tough. And they were like struggling with it, and they came to me and said, man, can you do this problem? And I just knew, man, that's a bear of a problem, And I just said, well, let's do a vector diagram. So I did it like, I used a compass. I did it in like 4 lines. And the answer was, reasonably close to the correct answer, because it's a diagram. And they were just like amazed. And from then on, they thought I was like some math genius. But it was just this bit that, vector diagrams are great, and they tend to be overlooked. If your life depends on getting the answer correct to 7 decimal places, I won't go near a vector diagram. It's got its uses. But don't assume that because it's not as precise as some of the other ways, that it's not useful, both in terms of thinking and also in giving you a quick approximate answer. They're really quite good. So what goes on? In principle, you have vectors. Now, what we're going to try and do with these vectors, we're going to try and add vectors, we're going to try and subtract vectors, we're going to try and multiply vectors by constants. Later on, we'll multiply vectors by vectors, but we're not there yet. So, examples. I have a machine tool, and the bottom axis goes that way, and I'm going that way at 5 meters per second. And riding on top of it, I have another gantry. So that slides with the bottom gantry. And your machine tool head is going that way at 2 meters per second. What's the velocity of the machine tool head? It's a combination of this motion and a combination of that motion. It's like if you've ever been on a boat, and the boat is moving, and you move relative to the boat. You're also moving relative to the water, because the boat moves over the water and you move over the boat. So it's this combination, and the way you find your motion is just add the 2 vectors together. That's why it's really nice. So that's the kind of game. Why would you subtract vectors? Well, why would you subtract vectors? Because something might be, well, why would you subtract vectors? Well, actually, what you tend to do is, in reality, you add the negative of a vector. If I have a vector in that direction and I want the opposite to that vector added to something else. I need to think of better examples of subtracting vectors. Anyway, so that's the kind of game we're going to play. In a way, vectors are very abstract. In a way, they're quite straightforward. We tend to start with vectors of displacement. So we have x and y. And we tend to talk in 2 dimensions to get going. And we kind of like visualize. So for instance, here's the United States, and here's Florida, and here's New York. And here's Tampa. And if I want to go from Tampa to New York, I'm going to move Tampa. Tampa's there. I use that's my displacement vector. That's my delta x. And because it's a vector, we put an arrow over the top. So there's my displacement vector for that. And that it's just the length. It's like a magnitude and a direction. So that makes pretty obvious. But you know, it can be quite sophisticated, because supposing I have a force system. So there's x and there's y. And I have a force in that direction. Now, the force is a magnitude pointing in a certain direction, and I represent it as an arrow. But it's not like you can move 3 meters to the right and look up and see the end of the force. You know, the force doesn't really have a length. It has a magnitude, but it doesn't have a length in space. And yet we're representing it as a length in space. So this is a bit of an abstraction. The force does not have a length in space, but we draw it as if it did. For the displacement does have a length in space. So sometimes, so what I worry about is, there's like 3 levels of physics. There's I just take everything on face value. You tend not to get confused. You know what you know, which isn't that much, but you don't get confused. And then there's people who think about it a bit deeper, and they start asking themselves questions, and sometimes they don't know the answer to those questions. And they've got to resolve that confusion. And they come out of it much stronger. So the 3rd level is when you've lived with this and tried to sort out these inconsistencies, and you're thinking, you're much stronger. I could tell you everything, and the fact is that you've got preconceived patterns in your mind, and you've got to uncomb those. And that's what the thinking does. You know, I tend to think that things slow down as they roll into the corner. I'm not saying it, but it's my background thinking. I have this idea about, you know, velocity with 0 acceleration. And according to the book, when I'm in the corner, I've got the same velocity, but things slow down. And even though I'm not saying to myself, but things slow down, my background thinking is saying, but things slow down. And so I get this inconsistency where the problem's telling me the answer's the same as here, but my experience is telling me it should be 0 or at least less. And if you don't think about it, you just do the math, and you know, you get this thing, and the answer's 12. Who cares what the answer is? It's just a number. So you don't worry about things, but you don't get any deeper understanding. But if you worry about things, why is this unsettling me? Because, you know, it's like I get the answer, I get the math, but it doesn't seem like it fits my gut. Then you start resolving the issue, and you know why it makes you uncomfortable, and you know sometimes you come across things you just didn't think of. And then you get much stronger. And I want to encourage you to kind of like do the good thing and try and think a bit deeper. Physics tends to seem easy, and then you start thinking about it, and it gets hard, and then you resolve those things, and it gets easier again. So I want you to go through this valley of, you know, discontent, because you'll be much more powerful engineers at the other side. And I'm not going to ask you what I explained, which seemed easy, because, you know, I'm going to ask you a different question. Other factors will come into place. Always that way. No matter which question I ask you, I'm not asking you only easy questions and then you're getting impossible questions. I'm asking you different questions. But, you know, if you've not seen that question before, unless you have that deeper thinking, you'll kind of go, man, this is really uncomfortable. And you don't want that in your test. Okay. And then so another example over here would be, we could have like a acceleration versus time. So it could be, you know, 5 meters per second squared. And again, you know, acceleration does not have a length, but we're going to draw it as if it has a length in these vector diagrams. So they are quite abstract. let's just stick with displacement to begin with. So here's a journey, and I start off with part A, and then part B, and then part C, and then part E, and then part D. And, you know, in the brochure, it would say, well, you know, you're going to do this journey, and you're going to do that 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 journey. And that's going to be journey A, and that's going to be journey B, and that's going to be journey C, and that's going to be journey D, and that's going to be journey E. So I might draw them not end to end, because the skill is, can you draw them end to end, you know? So I might represent them to you like that. Each one has a magnitude and a direction. And then your job is to add them up. In adding, it doesn't matter what the order is. So I'm going to do it underneath for this top one to show you another example. Then we'll do this example. So let's say I decided, I'm going to start down here. And let's say I decided to do B first. So let's do B first. And then let's say I did A. And then let's say I did D. And then let's say I did E. And then let's say I did C. Can you see how my answer is about the same? There's my answer for that one, and here's my answer for that one. The order doesn't matter. Okay, so not for addition. When you're doing subtraction, the order matters, but not for addition. Next thing. Vectors have arrowheads. They are not lines. They are arrows. And most common mistake is people will give me an answer which does not have an arrowhead. It just has lines. And that's not a vector. That's a big deal. Next thing. So the vector has to have an arrowhead on it. That's not good. Vector has to have an arrowhead on it. And next common mistake is the resultant replaces all those little steps. So the resultant starts at the beginning of the beginning and it ends at the end of the end. People sometimes put the arrowhead down here because they're closing the circle, closing the shape, and that's not correct. The resultant replaces those guys. It's like saying I flew from here to Orlando, and then I flew from Orlando to Miami. Then the person says, oh, so you flew from Miami to Tampa. And you go, no, I flew from here to Orlando, and then Orlando to Miami. And the equivalent is from here to Miami. So you've got to be careful you don't just close the circle. People tend to, in the diagram, close the circle. So what am I likely to give you? And what I'm going to give you is something like this, where we take this and you have to do it. I'm going to just pause this for a minute because I want to do a little bit of... So we just did a little break on the overhead so we could see what's going on. And basically what we decided was, let's name these guys. So this is going to be vector A, we put an arrowhead on top of that. Vector B, we put an arrowhead on top of that. It says find the resultant of these vectors. Not very well worded actually. These days I'd say find the resultant of adding these two vectors. Be a bit clearer. But basically what you do is I'm going to draw vector A. Now vector A I can draw. Do not use your old diagram. I think that's a mistake, especially if you have three vectors. It gets so messy. So do not use your old diagram. Just slide it across. I'm not perfectly parallel, but I'm reasonably parallel. And I'm not perfectly the same length, but I'm reasonably the same length. And then you take this guy down here, and with your ruler, I'm doing it freehand because that's all I can do here, but with my ruler, I'm going to go like that. And the process of addition is that the tail of the second vector starts at the head of the first vector. And so if that's vector A, that's vector B. And so my answer is res. And I just make it, I spend just a few seconds at the end making it very clear that I have arrowheads and they go in the right direction, especially the resultant. You need an arrowhead on any vector. But without an arrowhead on that resultant, I don't know which direction you think it's going in. It's not really even a vector. So you just got to do that. What about subtraction? Subtraction I'm going to do a bit of maths, sleight of hand here, and say vector A minus vector B is the same as vector A added to minus vector B. If that is vector B, that's minus vector B. The negative of a vector is the same size, opposite direction. So if that's vector A, that's minus A. If that's vector C, that's minus C. If that's vector D, that's minus vector D. Same size, opposite direction. So on this one it says, find the vector diagram A minus B. So I want to draw, B minus A. So I want to draw B. So I'm going to take that guy, I'm going to slide it across here. There's going to be my B. And then I'm not going to add A, but I am going to add, I'm going to add minus A. So the process of addition is I slide the tail until it's on the head of the original vector. Minus A. There's my answer. Do you see that? Can you see that? I took my B and I subtracted A by adding minus A. So minus A was down there. Yep. Start at the beginning, end at the end. There's your resultant. Cool. Want to multiply? If that's vector C, that's vector 2C. That's vector 3C. That's vector half a C. That's vector a tenth of a C. You just same direction, longer or shorter. So that's pretty straightforward. Cool. We're going to take a break in a minute, so well, maybe a couple of minutes. So basically, let's just do one quickly. So characterize the following as either Cartesian or polar. So what's this guy? Cartesian. What's this guy? Polar. What's this guy? Polar. What's this guy? Cartesian. Yeah, so it's that one. And then there's some examples. So using vector diagram, find the resultant of these displacement vectors. Do that one. Just do that one, and then I want to just draw it, and I want you to see. Are you lost, or are you okay with this? So do that one. So we're back. So I'm going to sort of add A to B. It doesn't matter which direction. So there's my A. The process of addition is put the tail of the second one on the head of the first. There's my B. There's my C. Res. Now, frankly, if you used a ruler and were careful, you'd probably get something like a 5 or 10% on your answer. You'd be all right. I'm going to skip that one. Do that one. Can you do that one for me, please? So for this one, I'm starting 2A, take away B. So that's going to be 2. Let's do our A's first. So I'm going to do, there's 1A, there's 2A. You could draw it as one arrow if you like. I prefer to draw it as 2 arrows, but there's nothing sacred about that. And then, oh man, well, it doesn't matter. Take away B means the opposite of B. It means add minus B. So the process of addition is I put the tail of minus B on the head of the A. I end up with that. This is minus B. So then I go boom, 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 boom. And so this is 2A minus B. Which is there. So can you see that? Make sense? That's the scale. Okay. That's the scale. You don't have to be perfect. Just have it the right, the right organization. I look and say, is it got the right shape? Well, I look and say, do you have arrowheads on things? Then I say, has it got the right shape? Is it about the right size, about the right angles? That kind of stuff. Okay. Let's take a 5-minute break. I'm going to upload this.